In this video, we're going to explore the relationship between pressure and volume, which are two of the measurable quantities that can be used to describe a gas. In all experimental design, we'll have to think about the other factors that could be related and then design an experiment that controls for those. So if pressure and volume are the two variables that we want to explore in this experiment, we have to think about an experimental design that will help us get at that relationship and not cloud the issue with other variables that might be a factor here by designing an experiment with proper control. In this experiment, we're going to make the independent variable be the volume. I think that's the easiest thing to dictate, to make sure that we know what it is ahead of time. And then the dependent variable will be the pressure, which we'll measure with the pressure sensor. We'll have to control for temperature because it may be true that the temperature would affect the pressure in addition to the volume affecting the pressure. That's easy to do because we'll be working in a heated, temperature-controlled space, so the temperature won't vary, or if it does, it'll vary very little bit during the time that our experiment is taking place. In a previous video, we found that the number of particles definitely affects the pressure, and so we'll have to control for that. Also, not too hard to do. We just make sure that the container doesn't leak as we're doing our experiment. We're going to use a gas pressure sensor to measure the pressures, and the volume we're going to adjust with a syringe. We can read the volume off the side of the syringe, and the plunger allows us to adjust the volume. Once it's sealed onto the pressure sensor, then no particles can leak in or out, so our constant number of particles condition will be met. Here's how we'll actually go about it. We'll draw in some amount of air. It really doesn't matter how much. Get some particles in there. Then we'll seal the syringe onto the pressure sensor, and after that we will never take it off. This ensures that the number of particles doesn't change. Then we can change the volume, take a pressure reading, change the volume again, take another pressure reading, change the volume again, take another pressure reading. So I've compressed the volume, made it smaller, but I can also go the other direction. I can expand the space that the particles fit in and take pressure readings at each of these new expansions and gather myself a good deal of data points. When I did this experiment with a number of different volumes, looks like I changed about every 2.5 milliliters, measured the pressure, keeping the number of particles the same, working in a constant temperature environment, I get these results. When I do a regression analysis, I find that a line is probably not a good way to describe the relationship between pressure and volume. You can see that the correlation value is 0.94, not really great. And the vertical intercept does not look like it's following the pattern here that seems like a downward curve. Hopefully you remember from your time in earlier science classes that what we do when we're presented with a data pattern that looks like this scatter plot is the first thing to explore is an inverse proportionality. So we'll take the horizontal axis, the volume in this case, and divide 1 by it. We'll take its reciprocal and then replot. When we do that, it turns out that it works. My correlation now has gone up to 0.9995. It's a very good reason to believe a line would be a good fit. The vertical intercept is not 0, it's 39 torr, but if you look at the highest pressure reading that we have, it's nearly 1500, and so 10% of that would be 150, half of that would be 75, so this is much less than 5%, and we can throw that out. So our relationship is the equation of this line. The vertical axis is pressure, the horizontal axis is 1 over volume, or inverse volume, and then the slope of this line would be our constant of proportionality. So this is the conclusion that we can draw. That constant value, the slope of that line, that's only fitting for this particular temperature and this particular number of particles. So it doesn't have a lot of value as a predictive tool. But if we multiply both sides by volume, we get a relationship that can be used all the time as long as the conditions of constant temperature and constant number of particles are met. So this is what that relationship would look like. Because the product of pressure and volume is a constant number, whatever happens to one of the variables, the inverse or reciprocal of that effect must occur to the other variable. In other words, if pressure increases by doubling, the only way that the constant can be maintained is if volume gets cut in half, and vice versa. So in conclusion, we could say that the main thing we learned here is that the pressure and the volume of a fixed number of particles of gas at a constant temperature is inversely proportional to each other. So whatever happens to one of the two variables, the reciprocal or the inverse must happen to the other. So if pressure triples, for example, volume must drop down to 1/3. If volume doubles, pressure must drop down to 1/2. It's an inverse proportionality.